Okay, so now back, you should be able to see the whiteboard and also it should be recorded. So, yeah, we will continue to talk about, or we are now moving in the regime to talk about probabilities. Probabilities. Yes. So, yeah, so all these things will come after our discussion of the probability mass function, probability density function, and then with those tools, also moment generating function. So with these tools at hand, then you will be able to talk about or calculating the specific numeric values of some to quantifying some uncertainties of some events, and also similar to what we have seen in the very first lecture where we have a real problem by dropping needles, and then by using all these mathematical tools and also statistical and mathematical tool, then we are able to calculate some numeric value to quantify some some random events and also uncertainties there to using a numeric value to quantify those. Okay, so that would be the idea for probability, but it all lays on the foundation on those mathematical function, the probability mass function, the density function, and the moment generating function. Okay, so as a quick recap, let's start with the binomial distribution. Okay, so this is a discrete case, and then we also have the x representing the count of success, or if you want to use the coin flip context, then it's just how many coins out of n tosses you will get the head. So we previously we kind of like invented the distribution from scratch by flipping coins. And one example is that we flip 3 coins and then we build a table, and then we come up with the we invented the formulation for the probability mass function of the binomial distribution. So what we have as a formula is that we have n tosses, and then we can have different location where the coins are landing on head and the remaining location are landing on tail. So the n choose k, this coefficient will handling that. And then this lowercase p here is the for each of the coin that landing on head, and then you need k of them because you observe k heads out of the n tosses or k success out of the n trials here. Similarly, you have the 1 minus p and then n minus k for those the failure case or the case that landing on tail. Okay, so we build a table and then we reinvent it from scratch for this probability mass function, a function that can describe that kind of random behavior. And then we also have the Poisson distribution. Similarly, this is also a discrete random variable, something to measure the count. And then we also have the formulation is equal to the parameter raised to the power or the counts that you have observed multiplying by exponential raised to the power of negative lambda and then k factorial. Yeah. So these distributions, they are for discrete variables, which means x is in either 0, 1, 2, 3, those integer, positive integer. And then it also have the parameters. So maybe I can put it here. Yeah, so one question that I have received is that how, or in practice, how do you choose which one to use? So my comments is that it's really is more often it's really up to your belief. How do you want to model the things? And then we have also seen that for the binomial distribution, when the limits for n goes to infinity through this process, this will become a Poisson. We also show the proof for this when the n go to infinity. So you can see that they are essentially, so they are highly connected to each other. And then in practice, it's more based on the user's preference or user's choice to choose which one to model or to measure the counts of interest. But for the let's say for the purpose or for the sake of answering homework question or midterm or exam question or textbook examples, another thing that I can provide as a hint just for the homework purpose or textbook purpose is that it really you can choose which one to use by their definition or by their parameters. So let me clarify that. So if you see a question or some, so in practice you will never get these, but this is just only for textbook or for question or answering homework problems. Then it's very likely the textbook or the question will give you some information. So if a question is giving you some either in words or also in mathematical formulas that you are doing n trials, and then the probability, the lowercase of success. Then this kinds of give you a hint to use the binomial distribution or binomial model to handle this particular homework question. Yeah. And then if it gives you like the average rate, more very specifically like a 2 calls per in our previous example, like 2 calls per minute in a call center, then it kinds of give you a hint of the Poisson distribution. So you can see that when you're working on the binomial distribution, there are two parameters that you need at least two parameters to use the formula, the density function, the probability mass function of the binomial. But for the Poisson distribution, you need one average, this lambda, to apply these density mass function here. So these are the probability mass function for the two. Yeah, but in practice, I mean, in real life, or in research, you usually don't get the luxury that these are given to you. You're just collecting patient data. But whether you want to represent the patient data as like n patients and then p probability of like a success or failure or something, or whether you come up with the average, that part is still based on your choice. Yeah, but just for the sake of answering homework question or textbook purpose, if you are provided these two parameters, then this kind of give you a sense to using binomial distribution. If this is provided, then it gives you a hint of using the Poisson. But as we can see in the previous example, where we connecting the binomial and Poisson by setting the lambda equal to n multiplied by p. So it just so again for homework purpose, it's just depending on which of these are given to you. But but in the back end, they are still connected to each other. Yeah. So that is one hint that I can provide it on if you're very interested or if you really want to have a way for the sake of the homework. If you really want a way to choose to see which one to use, then it depends on what information are given to you. But in practice, what people do is that they're collecting data, and then these are called, you have to estimate it. But the estimated is again based on your choice of the model. Okay. choice of the model. And then again, it based on whether you choose binomial as your model, whether you choose Poisson as as your model. So again, in practice or in realistic or in research, it's still based on your choice. Okay, so I hope that gives uh, um, kind of like a hint on how to choose. If that is really, if you really want to have like a guideline on choosing these. Yeah. Let me pause here and see if you have any question or comments because I have received a few question or comments on how to choosing this. Okay, maybe let me check the chat. Uh, okay. Yeah. So, yeah. So again, for the sake of the homework or answering textbook problems, so not in practice, like how things work in real life, but if you see something like they are handling or the question was asking for counts for something like what we have seen, like a coin flip, success, calls on the call centers or the earthquake examples, then if you see those count and then based on what you are given, well, you can still get the other one, or you can they are since they're connected. So you, if you want, you can always like manipulating them to get the parameters either NMP and also lambda, and then that will give you a hint. Yeah. So also a quick comments. So like binomial is like if you have n independent trials and then each with success probability of p. Yeah. So if you're given in some context like that, and also you are given with these two parameters, then you are safe to use the binomial mass function to calculate the probability of that event that the question asks you. And then for the Poisson, it's like was asking for the number of success. So this is kind of like the number of head that you can get over some duration. So usually for the Poisson distribution, it's more related to the time until like with related to time interval, that kind of questions. So yeah, so back then we relating them as when we cut a window with 60 time slot, and then let's say we're receiving three phone calls. So then it's kind of like, so in the binomial case, it's like in the n time slot, you have like a 3 over 60 as success for each of the time slot. And then if you're doing the Poisson case, then this is kind of like you are having 3 in this time window. Yeah. So this is how we connecting these two back then. Okay, but just for the sake of the homework or textbook problem or fake problems, then you can always use using this as your mechanism to choose which one to use. Okay, so maybe let me also give a quick example for the Poisson case. So here let's suppose the number of typo on a single page has a Poisson. So, okay, if a question is specifically asking you to do so, do it in the Poisson way, then this also give you a hint of using the Poisson probability mass function. So with lambda equal to 1/2. So now calculate the probability. This case is asking for at least. Okay, so later I'll comment a little bit on this at least case. At least one error on this page. Okay, so whenever you see this at least, this kind of problem, we have also seen this problem before, but let me just has a more of a like a elaborate again for when you see at least or at most this kind of problem. So the idea for handling these kind of problem when you have at least or at most something, the idea is to use the total probability, which is just equal to 1 for everything. So the probability that you have 0 error, 1 error, 2 error, or everything is an error, if you cover everything, then the probability of that everything will be equal to 1. So that will be for sure happening. And then in this case, it was asking for at least 1 error. So the idea here is that you want to use the probability of everything happen minus the case that it is not included in this case. So at least 1 error that is saying we don't want to include the case when there's no error, because 1 error, 2 error, or everything is error are included. The only thing that is removed from the total probability is the case when there are 0 errors. So if you minus from all the probability of everything, which is 1, by removing the case or the probability that there are 0 error happening, then you are essentially answering the at least case. And then if the problem is asking for at most 3 error, that is saying the case or the events that you want to calculate includes the following cases. You have 0 error plus 1 error plus 2 errors. Then you would just want to aggregating these 3 cases, because the cases for 3, so this is for at most 2 errors. So that means the number of errors like 3 or more, they are not included in your interest here. So you want to aggregate those. So depending on whether it's at least or at most, then you can always think about what are something or the counts here that are included, and then you aggregating them. So in our case, at least 1 error is saying that we want to remove the case when there's no error from the total, from everything that will happen, that is removing from 1. Okay. So previously we have seen an example with at most 2 cases. What we did before is that we aggregate these 3 things. But in this case, in this example, it's asking for at least, then you remove one. You remove the one that you don't want from everything that will happen. So that would be 1 minus p, the probability of you will see a 0 error. And then we know that it's from the Poisson distribution. So now, okay, and also for the probability of discrete case, the probability is just the output from the probability mass function. So the first step is that you choose. So the hint here already give you should choose Poisson. Once you choose the Poisson, the probability, and you identify this thing you want to remove. And then once you identify that, you want to calculate the probability of 0 error, then the probability of a discrete distribution is just the output from the probability mass function. So in this case, the probability of zero error is just the probability for this one. You want to use this formulation and plug in k equal to 0. So you will have, let me see, lambda raised to the power of k. Okay, so lambda is 1/2. Also, in textbook, they are usually given raised to the power of 0. And then e raised to the power of negative 1/2 over 0 factorial. And then this is equal to 1 minus. So anything raised to the power of 0 is equal to 1. You will have e raised to the power of negative 1/2. And then the 0 factorial by definition is equal to 1. You will have 1 minus e raised to the power of negative 1/2. And this should be about, so approximately 0.393. Okay, any question up to this point? Just a quick example regarding the Poisson. Okay, there's also no question in the chat. Okay, then let's continue on the continuous random variable. For these, we need to use the probability density function. And then we need to do one more extra step. So different from the discrete case, where, so this time x is in the real value. So it could take like 1.1, 1.21, 1.345. So these kind of real values. Then we need to use the probability density function. And then to calculate the probability, we usually referring the range. So in this case, we need one extra step, evaluating the integral. We usually talk about continuous random variable, and we are interested in their probability in a range. So here we have the x less than 1. So you need to go from the lower bound, integrate all the way to the number that so the number that you're interested. So sometimes this is called quantile, but let me not introduce those. So you need to calculate the integral up to the point of your interest here, and then plug in the density function dx. Yeah. If you're interested in the other direction, so anything after your quantity, that quantile or that value of interest, then you will start from the b all the way up to the positive infinity, and then integral dx. You can also calculating the range in between those. Then you need to evaluate the integral from the lower bound, upper bound, probability density function, dx. Yeah. So here, the f of x is the density function. And then you just need to evaluate those integrals. So the probability of a discrete case is just the output from a probability mass function. The probability of the continuous case is the integral of the probability density function. And also one thing we mentioned that we don't usually talk about the thing for continuous case that x equal to a particular value. The reason is that when you integrate from a to a, this one will always give you 0. So whether you choose to include these, it really does not, the equal sign here, it does not contribute, at least numerically, to your quantity of the probability as a number. So all these are probability that are in 0 and 1. Okay. So all these number will give you a number between 0 and 1 as your as a numeric value to quantify well, how probable something will happen. So, for example, if we consider the height of the trees, you might want to ask what is the probability that is less than 5 meters, or greater than 3 meters, or between 2 and 5 meters. So, this will allows you to answer that kind of question. And again, how you want to calculate the probability depending on the model that you choose. So if you believe that it's from an exponential distribution like what we did last time, plug in the density function for exponential. If you think it's a normal, plug in the normal case. If you believe it's a gamma, then you can also plug in the gamma case. Yeah. Any question up to this point?
Yes, I'd like to ask, how do you explain that um why the a specific outcome of a continuous random variable is zero by this method? Because even if, right, it's a continuous variable and it's between range of 0 to 3 and a is 2.51 yada continuous, um should it not be at least greater than 0, even if it's very small?
Uh, Sorry, I don't. Can you repeat your question? So your question is regarding, like, why is that this is zero?
Yes. Shouldn't it still be above 0 since A is a possibility? Sorry, is a possible outcome for this random variable?
Mm, yeah, that's a very good question. Um, Let me think of a good way to answering that. Mm, I think this is more from a um. mm,
I think it's that like it's possible, but it's sort of infinitely small. Like the other way to think about probability is the number of desired outcomes over the total outcomes. And then x equals a, that's like one possible outcome, and then your space being like, let's say 0 to 1, there's infinitely many numbers it could take on. So that would be like 1 over infinity, which becomes 0.
Yes, that would be one good way to answering that. Yeah.
Right, but then from a mathematical perspective, if from my limited understanding, if an individual slice is 0, how can the sum of a bunch of individual slices be greater than 0? Because yes, it is infinitely small, but 0 is the limit, which it should never reach. But if it does hit 0, then a to like a plus 1 should then still be 0 at least in my head, because it's summing up a bunch of really small slices, but each slice is 0.
I think it is supposed to be not actually 0. Like it's supposed to be some sort of limit thing, but we just call it 0 for some reason. I need to look up because I think there's like some reason that we're able to use that property to call it
I
0, but I don't remember it.
I think there's a three blue one brown video about this where it's like why probability of zero does not mean impossible.
Yeah, these are very great comments. Uh, yeah. So, um, yes. So, in the world of the mathematics, many things are uh, are highly counterintuitive. So, I think I would still well with the actually you guys already talk about the answer, so I think I'm just repeating from you guys. And one thing I, I kind of like the repeating part is that the idea of this integral to calculating the probability is like you're performing this operation, and the operation or the underlying idea for integrating things is that you are in cutting these like this function here. So this is represented by your function. You can draw a continuous function. And then the idea of this operation, which is called the integral or integration, is that when you're working on this continuous function, you cut them into different regions. And then you make them infinitely small, like the width of this triangle to be very, very small. And then the area here will eventually reduce to or collapse to a 0. So then it will not have a area. So when you're talking about a particular point in that, it's essentially like you gradually collapsing that area. So the area is coming from how you want to aggregating those, and then which is the integration part. And then when you only talking about one point, it's like you are collapsing or shrinking this area into a point. Then it has no area anymore, then it becomes a 0. But if you're aggregating these, then the area still exists, then the integration will give you this area here. But if you're talking about only one point, it's like we collapsing that area into a dot, into a point, then it has no air there's no the concept of area when you collapse the things into a dot or into a line from like a 2D thing into a 1D thing, then the concept of area disappear. Then we say that this is going to 0.
Okay.
So basically, I'm also just repeating what you guys were talking about, but in a more from a maybe from a visualization purpose and also by the integration. So integration here, so when we're talking about elements, when we're talking about summing of xi from 1 to n, we're just summing a 1 plus 2 plus 3. And the integration is just another way to summing things, but summing things that could be very, very small. And then in that case, in this continuous function, when you're summing things, you're getting this area. Sorry?
Oh, sorry. Somebody else needs. I was just saying bless you. Sorry.
Oh yeah. So when you are essentially doing the summing thing, but in a very small in a small triangles width and height. When you sum in the region and then when you collapse them into a dot, like evaluating from A to A, then the idea or the concept of area no longer exists. Then we give a value of 0 to representing that kind of case. So I'm not sure if that answering question, but it's also just repeating what the previous comments from you guys. Yeah.
Okay. Then a follow-up question. So then, if I understand properly, continuous PDFs, you cannot model specific outcomes, and PMFs can. So it's you have one for each specific case. It's not the case where a PDF can model both discrete cases and continuous cases. They are two separate
Yes.
functionalities.
Yes,
Okay.
exactly.
Thank
So
you.
when you want to talk about the discrete or counts or that kind of things, you always go to the probability mass function. For the region, for the areas or like a continuous case, we will need to talk about them in the domain of the probability density function. And then they are not kind of like not in like not overlapping. So we cannot talk about countings like a particular outcome in a continuous case. We can also not talk about a continue. So like count. So there's no like a concepts of I get like a 3.13 hats in 5 tosses. So these kind of the real value case, only the concept of real values only exists in this domain, and the concept of counts only exists in this domain, in the probability mass function. Yeah. So that's why I started by talking about there are 2 branches, discrete, continuous, probability mass function, probability density function, and then so they fall when we measure the random phenomena here, it breaks into those regions, and then these will lead to probability, which is what we are going to discussing now. Yeah. So there are 2 branches, 2 separate regime.
Thank you very much.
Yeah. Yeah. So everything is originated from the probability mass function and the density function. And then their connection is going through the moment generating function. Yeah. And then after that, we are ready to talk about probabilities of those things. Yeah. Yeah. And then integration is just another way to summing things when it's in the continuous case. Yeah. Yeah. Maybe I will keep these for now. Yeah. Yeah. So when it collapses, the concepts of the area no longer exist. We replace by 0. Yeah. And then this is only for intervals or regions. Yeah. Okay, so next let me do one example like last time for the exponential distribution. And okay, so now let's start with another example. I think we have 15 minutes. Okay, so we will be able to. Okay, just one quick example similar to last time. So based on, and later on I want to talk about normal distribution. So based on historic data, major earthquake happened at a rate of 0.002 per year. Okay, so based on this question, we are giving kind of like a rate. And now let's take a look at the question that we could ask. So let's say question A, what is the probability that there are 0 major earthquake next year? Okay, so now we are, here are, you can consider them as past data or the prompt in the from the question. And then here we also have, we are interested in the probability. So that means we need to do some calculation. We are interested in the probability of 0 major earthquake. So in this case, are we talking about discrete things or continuous things here? So now we're trying to identify whether we should go into the probability mass function regime or the probability density function regime before choosing what model to use. So in this question, are we in the discrete case or the continuous case?
We are in the discrete, we're in a discrete case because we weren't given.
Mm-hmm.
We were, sorry, I thought I heard no, so I was like, oh, okay. We're in a discrete case because we're given a rate, and if it was continuous, then we'd be given number of successes or events in a given time frame. But because it says rate, it's discrete.
Mm-hmm. Yeah, so yes, we are here working in the discrete case. And yeah, just like you said, this is because the question here was asking related to like a specific count for a for the probability of a specific count things. So we are interested in the probability. So if we write it mathematically, it's like we want this thing happen. We are interested in the probability that there will be zero, like zero head or zero success. So then we are in the discrete regime. And just for a comparison, let me also write down the second question, and then maybe that will also make it even clearer for the differences. So my second question, so before answering part A, let me just write down part B. So what is the probability? Okay, so now all the question all start with calculating the probability. And then that a major earthquake occurs in the next 30 years. So for question in part B, do you think this is in the discrete case or in the continuous case?
Discrete.
Why is that?
Because we're given this is giving like a number of coin tosses essentially. We're flipping 30 times because we're given a rate in the form of years, and this is also in the form of years. Or it's also as a measure of time. So then it's flipping a coin.
Okay. Actually, I would consider the part B as in a continuous case. So this is my my thoughts. So for the first one is the discrete case, and then for the second one, I would consider it as a continuous case. So the reason is that in the part A, we are asking the probability that a zero earthquake happened. And also when we write down, if we write down in the mathematical language, this is something that we want to evaluating. We want that the counts of the earthquake exactly be equal to zero. And in the second case here, one reason I consider it as a continuous case is that a major earthquake occur in the next 30 years is that when I think about this in a time window, so from current time point to the next 30 time point, to the next to the 30 years away from now, is that the major earthquake can happen in here. And it could also happen in here. It could happen at the first, exactly on the first year, but it could also happen on the 1.5 year. It could also happen in the 1 year, 3 days, and also like a certain month and certain day. So in that sense, then we are kind of like thinking the time, the earthquake from in this time window at any location, but as long as within the 30 years. So in this case, then we are considering the events occurring in this real continuous or real lines or continuous time span. Then I will consider that the probability that it happens or occurs in the next 30 years, because it could locate at any time point in a continuous time window, then I will regard this as a continuous case. And that is my reasoning here. So I think also as a like a homework or like for answering question in the midterm, another thing to give it away is kind of like if we're just directly doing the counts, then we are talking about discrete case. And very often when we're talking about something about in the time, and then it could happen any time in this time window, then it's very likely it's in the continuous case. So that would be my reasoning here.
Professor.
Yeah.
Um, by that same reasoning, wouldn't A also be a continuous case because it's asking within a given time frame? It's not asking at a specific given moment. Thus, by that same logic, should A not also be a continuous case? Sorry, yeah, continuous case.
I think for A it's more specific that it's just exactly equal to in zero.
Right, but then in B, it's P of X equals 1. And then is if so then I was thinking we could plug it in as N is equal to 30 and X is equal to 1 for the binomial distribution. And so in my head, it still follows the same form. Because,
Mhm. So for me, in the second question, I will write down a mathematical formulation in this way, is that the is that the the timing for this for the next for a major earthquake would happen in this time window between from now to 30 years away. So uh yeah, and also yeah, so that would be my reasoning. And also one thing is that the thing is that when in natural language here, it could cause um lots of confusion here. So if I directly writing down this one, I ask you to compute, then we immediately know it's a continuous case. So I think the confusion here is that how we transferring the natural language that like the things that we describe something in words and in text and how to convert it into mathematical language. So maybe this sentence here, the question here is not precisely not very precise. So the most precise so mathematical language is very precise. If I write down this, there's no confusion. But if I write down a sentence, it could cause confusion here. So maybe one thing I could comment is that maybe the question here or this from the textbook is not well written in this in the way that in this sentence, because this sentence can be read in different ways, so it could cause very different meanings. But the thing I want to point out is that we are still interested in the things that happening anytime in between this 30-year window, so that will consider as a continuous case. But again, it could be this textbook or this question is not well written in the natural language sense. But if we but if the question was asking for calculating this, then in the mathematical language, then it would be very precise. But I think maybe the text or yeah. So the thing I want to mention here is that we still want to talk about the continuous sense of a time span for the part B. Yeah, but maybe it's because the question or the wording here in the part B is not precise enough. Yeah.
Professor,
Yes.
I don't want to beat a dead horse, um, but couldn't we phrase A then as the probability of X being between 0 and 1 inclusive?
But we are still interested in the counts. That is exactly zero. There's zero earthquake.
Right.
Is it
No.
that Are we saying X is the number of earthquakes and Y is the time before the next earthquake?
Yes, that's a good point. So when you're introducing random variables, you have to define properly. So here is X is the number of heads, let's say in the coin flip, and then Y is the timing, or well, you see, when we're using natural language, things will get will be confusing. So it's like the timing that the next earthquake happening.
Yeah, I feel like then it could be interpreted multiple ways. Like you could say that A is equal to the probability that Y is greater than or equal to 1, because if it takes more than 1 year for an earthquake to happen, then that means
Okay.
an earthquake didn't happen this year.
Then maybe I will write down exactly 0 earthquake. Then maybe that could also help. But it's that how you interpret the question and convert into mathematical language here. Yeah. So
I
would it
might,
be
once you give us the formulas, I might try to calculate it both ways, and then maybe it'll be the same answer. Because if you can interpret it two different ways, then ideally, if those two interpretations are both correct, then they would both be the same answer.
mm, the thing is that for the part A, this is for discrete case, so you can only measure calculating that the P, the probability of that in the from the probability mass function. So yeah, so I was still going back here is that this is asking for exactly 0 earthquake. So we want the discrete probability mass function. And here, a major earthquake occur in the next 30 years or maybe within, maybe. So it really depends on how we choose to write things in words. So then it could causing the differences here. And then in this case, I want to measure the probability of y between 0 and 30. So it's a continuous time window. So I will still, so yeah, so that would be how I would consider this question. So maybe we can talk about this later, and let me just finish the calculation here, and then maybe we can talk about these later. So in the discrete case, x equal to 0, then one thing is that you can use the Poisson distribution, and then you will have the lambda, negative lambda, 0 factorial, plug in lambda, the rate equal to 0.002. This will give you the probability of 0.998. So with a rate that an earthquake happen per year with a rate of 0.002, it's highly unlikely that it will have an earthquake. So you can see that the probability that no earthquake is relatively high here. We have a 0.998. So here, this is discrete. We want exactly 0. We're talking about a discrete random variable. And then also intuitively, with a rate of that small, then in the next year, the probability of happening is very high. And then for the continuous case, so here I'm defining y as the timing. It could happening within that one earthquake happening in that 30-year window. So what I'm doing is that we want to integrate from 0 all the way to 30. And then for this one, we are going to use the exponential distribution to measure the discrete case, the continuous case, lambda x dx. And then when you evaluating this integral, like what we did last time, then you will have the formula from the e of the lambda. So here I use letter y, so maybe I will just stick with the also dy. Yeah, so just to mention, this is the probability between 0 and y. So here I'm defining the y as like the timing. It could happen anytime within that 30-year, like whether it's like 1.5 years away, 1.1155 years away from my current time point. As long as within the 30, that gives you an upper bound, lower bound, then you can calculating those. And here the lambda again is the 0.002 multiplying by y. And then we need to evaluating that from 0 to 30. And so last time we derived this anti-derivative. I provided a formula in the last lecture. And then if you plug in this number, you will have 1 minus e to the negative 0.06. This will be the probability of 0.06. So you will have a probability of 0.06 that there will be an earthquake happening in that 30 years time window. Yeah, the formulas here or more details are in the last lecture. Yeah. So yeah. So this is what we did in the end of the last lecture, when we are using the exponential distribution to talk about a continuous time frame here to answer this question. So for the first part A is that we are talking about discrete, exactly 0. The second part is that we talk about any time happening in this window. So we have a continuous case, and we choose the exponential distribution like what we did last time. And then to answering this, all we need to do is just one extra step, calculating the integral here. And yeah, any question or comments here?
Can you use another distribution like besides exponential?
Yes. So again, that's a very good question. So if you want, so exponential distribution have this density function f of x. So another thing is that you can also use gamma distribution. So one quick, just to answer that question, the moment generating function of the exponential distribution, back then we provided 3 versions, and this is one of the version, 1 over lambda t negative 1 back then. So that's the moment generating function of that. The moment generating function for the gamma distribution is 1 minus beta t negative alpha. That's a moment generating function for the gamma distribution. This is so the exponential distribution only have 1 parameter lambda. The gamma distribution have 2 parameter alpha and beta. So again, it really depending on whether the question have give you. So again, these are all just textbook example. In the real world, you will never be provided like, okay, so calculating this with lambda, that calculating this with alpha beta equal to those. So these only exist in the textbook. So in the real world, you never know how do you get a rate of 0.002, and that's 1 lambda. And so yeah, so that only exists in the textbook. So as long as you are able to have one parameter that related to the rate, then we use exponential distribution, like what we did here. The thing is that you can also use a gamma distribution, but you need one extra step to rewrite or to think about this question here from your data or from the information that you have. So the thing for the gamma distribution is that now let's comparing their moment generating function. You will see that the exponential parameter distribution with parameter lambda is essentially the same as the gamma distribution, where alpha is equal to 1, and then beta equal to 1 over lambda, the rate that you have that is given in the prompt or in the question. Then once you recognizing these, then Of course, you are allowed to use gamma distribution. What you need to do, again, 0 less than y less than 30. Here, from 0 to 30, f of x here, dx, or f of y, dy, just a choice of letters, dy. Here, instead of using the exponential distribution, plug in the gamma probability density function. That's the only thing you need to do, but you just need to recognizing this thing here, and or whether the question give you gamma, lambda, the parameter, or the question giving you alpha, beta. Otherwise, the way that you choose which one to use depending on what information that you have at hand. So if the information or the question provided you like n trials p, the probability of success, then it gives you a hint of using binomial. If it give you the lambda, then it give you the Poisson. And here, for the continuous case, if it gives you the rate, then you can use exponential, or through some manipulation, you can use the gamma distribution. Yeah. So you can also use gamma to handling this question, because exponential is essentially a special case when alpha equal to 1. So you can also use other density function. It just depending on what information you have, and then whether you are able, if you choose to use gamma, are you able to calculating those, or with sufficient information to quantify that or to enable your calculation? Does that answer your question?
Yeah, I actually had a follow-up one. So like you wouldn't be able to use normal here unless they tell you.
Okay, so the things in the normal case is slightly different is because, so everything again is all based on the foundation of the probability density function or probability mass function. So to answer your question regarding normal, let's revisit the support for the exponential in gamma. The exponential distribution n or gamma has the support of x greater than 0 for real value. The support for normal is x in negative infinity to positive infinity. In this context, we are talking about the time. So we're talking about something happening from 0 or 30 years away. We are only talking about, or the context here only makes sense when we have like 5 years away or 5.1 years away. But does it make sense to talk about negative 5.13 years away? Then in the time in this context may not make sense. So then we would normally not using normal distribution, which cover the whole real lines here. So in this case, the normal, you could also use the normal only using this half of the normal, the 0 to infinity part, to handling that. That is called truncated normal. So in the real context, you will need a truncated normal to talk about that. But in this case, because the negative part may not make sense in this context, so we may not favor normal to estimating that. And also, you need to know what is the parameter mu and the sigma, even if you want to use the normal. So you need extra information to use that. Does that answer your follow-up question?
Yeah, thank you.
Yeah. So mathematicals, these are the tools that we provided for handling things. But now, when we now move into the regime probability, it would depend on the context and also the natural language that the things that are provided or are asking you. So things would get so yeah, as you can see, now we're gradually moving to the real things. Then it could it would depend on how we choose the mathematical tools.
So just to make sure I understand, we could use the Poisson here, right? We could use the gamma, we could use the exponential. Is there any preference in this case between Poisson and gamma? I'm just excluding exponential and gamma.
So again, in real world or in real analysis, or I mean, not the not mathematical real analysis. So in real world analysis, um, there isn't really like a specific rules to choose which one to use. You sometimes people choose using many of both of them, and then to comment on their differences, and that would be for the research purpose. But for the textbook purpose or for the homework and midterm exam in a school setting, then it's just based on what information you have or what the question is asking for. So if the question only providing you lambda, then you only have this information to answer this question, then 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 that's what you have, then you can only choose the Poisson here. But if you have, as a researcher, then if you other ways to collecting data, new information, or if you have a way to manipulate this, setting this lambda to n equal n p, you can get the n, get the p, then you'll be able to extending your analysis here by using binomial to replace the Poisson. But in practice, there's no preferences there. But in the question, in textbook, or in a educational setting, then based on what the question is asking, what information is provided to you. Does that answer your question?
Yes, thank you.
Okay, so in the last 20 minutes, there's one important thing I want to focus is the normal distribution. So the normal distribution, we talk about those, we derive homogeneous functions. Now I just want to talk about one more things. Okay. Maybe here. So the normal distribution is used to talk about continuous case. So the normal density function, so you can look up the notes from before. It has two parameters. Let me put here a semicolon, mu and sigma square. Okay, so to describe a normal distribution, you will need two parameters here. Like the gamma, you have two parameters. Like exponential only have one. So the parameters here are the key things. Like if the question provided you, then you can describe or choosing the normal or the density function that you want to use to calculating the probability of interest of the events of interest. So here you have a normal distribution measured or provided or can be described by two parameters. And here is that the mean. So back then we spent a whole lecture to talk about the expected value equal to mu, the variance equal to sigma squared. So the variance here would be defined by how wide. So you have variability of those. And then if you have a smaller variance, then it's very likely you will have a thin normal distribution because you have less variability. So everything is kind of like will for sure happening in this region, while in this one you can happen in a wide, have a larger variations. Okay, so when you have the two parameters, it will first define the location and the variance. Okay, and then one thing here is that we talk about the transformation, the z equal to x minus mu scaled by the variance as the standard deviation, the square root of the variance. Okay, so here let me just provide a quick visualization. When you minus the mu, so you can have your x1 here, x2 here, x3 here, and lots of x here, lots of random variable that can be described by this shape. When you minus the mu, you're essentially just moving everything. You're moving the same shape here. If I can copy paste, I'm just moving here everything toward 0. So all of them are centered around 0. but they still have the variability that is described by this variance here. So now, so for here, maybe I can put it here. So the expectation after you moving toward, so we're shifting to the left, or if your mu is starting from the left-hand side, then you're just moving to the right, but moving toward the 0. So now your expectation has been moved to 0 through this transformation. And then your variance stay the same. Okay, so this is the x minus mu part. Okay, you can also show this through, again, everything analysis here can be done by moment generating function. You can also show that when you minus or shifting by mu, you are just affecting the expectation. Then the moment generating function can show that. Now let's handling the denominator part. So let me draw from here to here. And later I will talk about why this transformation is very important in your calculation in the normal cases. So when you further scale by the standard deviation, the variabilities of your random phenomena here, you will still have a normal. Again, whether it's the normal distribution, check through moment generating function. Okay, you will still have the mean equal to 0, the expectation equal to 0, the variance of now is equal to 1. And this is called the standard normal distribution. And then if you have x following general normal mu sigma square through x minus a mu, so pulling everything toward 0, scale by sigma 1 over sigma x minus mu to get the z. Here, scale by that. You will get z following a standard normal. So the variability here will have is a constant. It's fixed. So the sigma now equal to 1. But here, all these sigmas are for the mu and the sigma for the x. Here, the sigma is for the z and then the mu of z. So if you want to be precise, so now you should, after the transformation, you should write the expectation of z equals 0, variance of z equal to 1. And what you can replace here is the expectation for x dragging toward minus mu over sigma. So we're just replacing the z by its formula from the x. X minus the mu over sigma. And then you're just, essentially, you have something that describes the height of trees, but in this case, maybe it's not make sense to have a negative 5 meters, but let me just like something that as a very abstract, maybe not use the height then, something that can be measured both negative and positive value, and then if you drag by mu, so you are moving toward the 0. Scaling that variability, that random variable, you will reduce your variabilities into a constant, which is a 1. And then you will end up with the standard normal here. Okay, so this is called standardization. And then all these things we have also talked about the moment generating function of those in the previous lecture. So you can resort to your previous lecture note to get all these regarding the transformation and then the moment generating function of these components here. But here I'm just giving a visual explanation of what we did before when we introduced the normal. Okay, so the thing here, when this one here is important, is that now when you're given a question, and let's say the question specifically tells you, you can use the normal, mu and the sigma square. So the prompt already tells you, you can use this to measure some random behavior. So let's say x following a normal with mu equal to 3, variance equal to 9. Okay, and now the problem is asking you calculate the probability of p less than x. So you can either adding the equal sign or not, it doesn't matters. If you want, if the question I told you, you are given the normal, you need to calculate this by normal, and this is the event you're interested. And now let's see how we can handle this problem and how the transformation play a role here. So you are again the definition. So to calculate the probability of something in the continuous case, setting the lower bound, upper bound, density function, dx. But if you plug in the 1 over 2 pi sigma square, where sigma square is the 9, exponential, negative 1/2 x minus mu, your normal density function, dx. Comments, this is extremely difficult or even not feasible to calculate from the integral. So what we can do here, the solution, standardization. Okay, so again, we're interested in this thing, but you want to calculate the probability through the integral, extremely difficult or even not feasible. There's no analytical solution for that. What you can do is that drag your lower bound by the value mu, standardizing that, less than your actual variable that you quantify the things that depending on the context here. So here we don't give a context, so we'll just use x minus the mu, standard deviation, less than 5 minus the mu. And here the mu and the sigma square are already given to you. So you have those values. So again, these are in textbook or in homework problems, these are given to you, and then you can just plug them in. And in this case, so the equal sign holds, but what you did here is that 2 minus 3 over 3. And you convert this into a standard normal with the mu equal to 0 and sigma square equal to 1 now. 5 minus 3 over 3. The 3 is coming from the square root of 9. Okay, and then you can calculating negative 1/3 less than z less than 2 over 3. So this one, if you want, you can also use the integral to calculating that dz. But again, difficult or not even feasible. Then how should we solve this? So the idea is also the intuition or the underlying result is also based on in the history. There's no way or there's no computer at all to calculating this. So resorting to a Z table. So now let's take a look at the visualization here. After the transformation, we have the center around 0. And we are interested in the region -1/3, 2/3. That is saying, when we perform this integral here, the things that we're actually calculating is that we are accumulating the area here, where this is defined by a continuous function, the probability mass function, the probability density function. Okay, you're interested in this. But again, evaluating this integral mathematically is difficult. Back then, when there's no computer, they resort in a Z table, and then what we can do is that once we have these also obtained from the transformation, let's resort to the table. I'm showing a table here. Are you guys able to see it?
Yes.
Okay, so the value that we want, so here you can see that on the top it says this is the area to the left of the z-score. So the z-score that we have after we transform the problem is the -1/3. So -1/3 is about -0.33. So by using this table as a dictionary back then when there's no calculator, people come up with this table. We know we want the area of the 0 point up to 0.1/3, 0.33. So that means we go from the bottom, from the rows, we have the -0.3, and also we look for a column for the 0.03. That means, so I'm not sure if you can see here, 0, 1, 2, and 3. That means it's this number, 0.3707. So this is the, on the row, we have the -0.3. On the column, we have the 0.003. Then we identify this number, 0.37070. Okay, look up the dictionary. This is a dictionary. Look up the table. The number that we obtain is for the for the standard normal. The table tells us up to -1.3. This region is 0.37070 based on the table or a dictionary, if you want. Okay. And then let's hold this information for now. We also want this one, 0.66. Okay. Now back to the table. What we have is 0.66. What we need is 0.66. We can see that 0.6012345 is this number. 0.25463. Okay, 25463. The other number that we get under this is negative 0.254. Can someone also just remind me 254? Okay. 254 254 254 25463. Okay, the table providing us these two values. Let's see how we can get those, how we can get the answer for this problem. First of all, is that the normal distribution is symmetric. The reason it's symmetric because of the probability density function defines the symmetric there. So again, everything centered around probability density function. If you know negative 2/3 has the area under the curve equal to that, that means this region 0.25463 due to the symmetric. Okay, so now what we have, the information that we collected so far is the region in the lower tail below negative 1/3, and also the information after more than positive 2.3. Then here is the question of interest, the problem of interest we want. How do we get the targeted region? The resulting underlying or the idea here is that the everything under the curve is 1. The whole thing, everything happening has a probability of 1. We know the left tail 0.2537. We also know the other tail here 0.25463. The only thing that we want is the middle part. Okay, assuming that these three shapes look the same, okay? So to get those, 1, which is here, property 1, minus the left tail, minus the right tail. Looking from the table, obtained from the table, plus some tricks on the symmetric, this will give you about 0.3779. But just using a calculator to do that, and then you will get the probability. That will be the answer for this one, 0.3779. But this one is also obtained by just manipulation. So the original question give you 0.3779. And then you'll be able to answer the question, what is the probability of this one here? Okay, so the trick is that if the problem already give, or in your context, you know that you can handling real value, negative infinity to positive infinity, you choose a normal. The normal, you need to use the definition of the probability, which is integral, but this thing has no analytical solution. Back then, when we introduced the expectation, we spent the whole lecture and lots of tricks to handling though. So you already know that it's very difficult to calculate the integral. But we still want the probability. So the people back then, they do not have computer. Then they created this table that you see here. That will give you to the region under the standard normal by these quantile or these values. And then you can use the tricks like removing those and knowing that the whole thing equal to 1, removing those, obtain the probability. That will give you the probability of your original question, which is here, part A, your question. Okay, so let me pause here. That will be all for today. Yeah. I'm still in the office, so if you're on campus, feel free to stop by. But I'll just pause here. Yeah, thanks.
Thank you, Professor.